Okay, so we're going to go ahead and start to take a look here at example number 1 and see how kind of everything that we stated up above can kind of be played out here. So let's take a look at what we got. A college is interested in looking at whether or not students complete their associate's degrees. A sample of 1,105 male students showed that 387 complete their degree, and a sample of 4 female students showed that 568 completed their degree. Is there a significant difference between the completion rates of males and females? Okay, so this is the question. You know, a certain percentage of males are going to, graduate, finish their degree. A certain percentage of females are going to graduate and finish their degree. And I might want to know, are these like pretty much the same percentage? Are they different percentages? Is one higher than another? So before I even start writing hypotheses here, I might want to try to distinguish these two percentages. So I'm going to start by writing this. Since the male students were listed first, let's have P1 stand for the percentage of all males that complete their degree. And then I'll have P number 2 is another mystery percentage, which would be the percentage of all females that complete their degree. Now again, I have no idea what these percentages are because these are the overall values. I did not survey all of the males. I did not survey all of the females. We surveyed some of them. So the numbers that are given in the problem will not help us directly determine these percentages. But I want to make hypotheses about these percentages. And so I'll start with H0 and H1. Now the best part is H0 is going to look the same every single time. It's going to say that P1 and P2, well, they're identical. And we want to test, according to the problem, if there is a significant difference between the completion rates. We don't want to test to see if one is bigger or smaller than the other. We want to test to see if these percentages are not the same. So these are our black hypotheses. And automatically we should be aware that there is kind of then an implied green hypothesis. Very oftentimes we will never even write this green hypothesis, but it's important to be able to think about in certain moments. So notice that if I subtracted P2 to the left side, this is what I would end up with for my green hypotheses. Okay, now we're going to go down to our test statistic and start to write out some of our sample evidence. Okay, so I'm going to start by taking a look at the males. So I should have surveyed a certain number of males, and that looks like that was 1105. A certain number of males completed their degree, and so I should get a p hat number 1, which would be from 387 over 1105. Now for the sake of time, I'm going to go ahead here and just write out the values that I found, but you can double check me with your own calculations. I found that percentage to be 0.3502. Below this, I'll just write down exactly what I got for all of my second sample values. So there were 1,234 girls that were surveyed. There were 568 of them that completed their degree. And so p hat number 2, I get by doing this division. And I got this value as 0.4603. So these are all the values that I have thus far, but there's one other one that I need. And it's p hat number 1 minus p hat number 2. I'm curious what the difference between my p hats is, because that's the only way I can start to see if this H0, which says that the difference between the p's should be 0, if that's like a good fit or not. So notice here that this isn't too hard. If I went to my calculator and I typed in 0.3502, let me pull up my calculator here so I can actually do it. But I do 0.3502 and I subtract the 0.4603, then p hat 1 minus p hat 2 gives me a negative 0.1101. And it's okay that the result is negative. There's nothing weird about that. Okay, so I have this portion done. I have all my given information down. What I'm curious about, though, is this a rare subtraction of p-hats to find, or is that pretty common to happen by just chance? So to determine that, I'm going to have to do some checks so I can figure out the distribution of p-hat 1 minus p-hat 2. Again, the checks here are really, really annoying because I'm going to have to do 20 times my first sample size. I'm going to get that value to end up as 22,100. And I'm going to ask, is that less than or equal to the total number of like all possible male students? Well, I don't know that value. It seems pretty reasonable that if this is looking at all students, sure, there's a lot of students that go for associate's degrees. If I was to go ahead and take a look at what happens with sample 2, I see that I end up with 24680 when I do that multiplication, and when I believe there are at least this many female students, and absolutely I do. I then have 2 more checks to actually conduct. These would be the checks where I have to take this value times the believed value for, or times the value for p hat, which in this case is my 0.3502, and then my 1 minus my 0.3502. And I want to check to see if that is going to be greater than or equal to 10. I ended up with 251.4538, and so indeed, this is bigger than 10. When I check for the females, I have to use the percentage 4603, and then 1 minus 0.4603, and I end up with 306.5551. Okay. So it seems like all the checks have been met, and so as a result, what I can actually go ahead and attempt to do is to say that p hat 1 minus p hat 2 has a normal distribution. So this is great news. I'm pretty much done with this step. The checks are the worst part. The last thing that I'm going to have up here is a z-score that I need to compute. But again, I'll compute that as I start to draw my picture down below. So here's what I have. I could imagine up all my p hat 1 minus p hat 2's on a number line. Some are big, some are small. And I know they fall into a normal distribution. I can think now that since I'm believing that h0 is true, what would I expect to happen when I do p hat 1 minus p hat 2? Well, if h0 is true, then when I subtract my p's, I should get 0. So I would expect that when I subtract my p hats, I should also get 0. So I'm going to have a 0 here. But of course, I didn't get 0 when I did my p hat 1 minus p hat 2. If we look back up, we'll see that we got negative 0.1101. So that would be like a number over here on the number line. And we're going to be curious right now if that's a percentage that's too low. Although we also have to double check, since we have a two-tailed test, remember if that's a percentage that is also too high. And when I put these two values together, I create the p-value. I can also go ahead and state that that p-value is going to apparently be equal to the chances of getting a p hat 1 minus a p hat 2 less than my negative 0.1101. And that would correspond to the area over here in the bottom left. But since that's not all the p-value and the distribution is symmetrical, I'll just multiply by 2, and the calculator will remember to do that. Other thing I can list on here is my z-scores. I already know the z-score for 0 is 0, but I don't know the z-score for my difference of p-hats. And of course, the calculator will take care of all of this. On the calculator, I can go ahead and I can start to run my test. My test right now, remember, is a 2-proportion z-test, which is right down here at example number 6. If I click on this, you'll notice that it asks for all the information that we already wrote down. 387, 1105, 568, 1234. And notice again, it's got this fill in the blank template for my alternative hypothesis, which in our case was P1 is not equal to P2. If I go to calculate, notice immediately it tells me my z-score, negative 5.4067. Negative 5.4067 can be added to the picture. I also see my p-value, which looks like 6 point, wait a minute, 6 point. I can't have p-values that are, I mean, that's a probability. I can't have probabilities over 1. Oh, wait a minute. Remember, if you get a probability that's over 1, you got to read all the way to the end. I have an e negative 8. This is going to be a decimal like 0.000. So far I'm at 4 zeros, 5, 6, 7, 8 zeros, and then my decimal would start. Of course, if I was to round that off to a couple or to 4 places, that's roughly 0. So the chances of us getting this just by luck is next to nothing. That's even indicated as well by the fact that this z-score is really large, right? That's many jumps below average. So my alpha value on this problem was given as 0.05, and it looks like I definitely have a rare sample. So when we have a rare sample, we said before that we don't think then that H0 is a good fit, and we're going to reject it. I'm going to write my 2-sentence conclusion just like I always do. So here's what we'll say. It is rare to get a difference of sample percentages of negative 0.1101 by chance if the real difference is 0. That's exactly what we saw. It was weird to get our blue value, assuming that the real difference was 0. So we can then conclude, therefore, we have enough evidence to believe that H1 is true. But we don't want to write H1, so we'll write down what H1 actually said in words. Notice H1 said P1 and P2 are not the same. But if P1 is the percentage of all males that complete their degree, and P2 is the percentage of all females that complete their degree, I could maybe write something like this. We don't have enough evidence to believe that the percentage, we have enough evidence to believe that the percentage of males and the percentage of females who complete their degree are different. You could also say are not the same, are different numbers, different values. Well, there we go. This is actually hopefully really good news because you'll see here, doesn't a lot of this question seem almost identical to all the other hypothesis tests that we've done? There's a couple small minor modifications, but for the most part, this is completely consistent with all the other questions. Now, what I'm going to ask you to do is to take a look at examples number 2 and 3. In class, these would have been problems that would have been left for you to try to complete. And so I'll ask you to try to work through these on your own and check the solutions that are up online. In the next video, I'm going to take a look at example number 3, continued, which will be the first instance of where we will try to use hypothesis testing using confidence intervals in this section. And I'll see you in that video.